So we were finishing up this one last time. Let's talk about it. So what did we started with this function right here. First we had x as a function of y, and that was x equals ln of y. That was the g function. And we said we're going to rotate that, and that was from y from 1 to 4. So we're going to rotate that around the x-axis and create a surface, right? That was like a funnel or like a horn, right? The bell of a horn. Okay, and so we were looking at first arc length, but then we're looking at surface area of this funnel, and we came up with using y as the independent variable. We were doing y as the independent variable, but our ribbons still would go around this way. The ribbons are going to follow how we rotate the curve, but then we can choose to have y increase through delta y intervals or x increase through delta x intervals. But that doesn't change the ribbons, right? So the ribbons are still... Why isn't that writing? There we go. The ribbons still look like this. So we did y increasing through delta y intervals, and we got this function for surface area. So I'm gonna pick a point here on this graph, and the point is 1.36, comma, basically 3.50. And so I want you to tell me tell the person next to you, what's the meaning of that ordered pair on this graph? What's the meaning of that ordered pair on this graph, 1.36, 3.50? And so all the details about those numbers. What is this number? Exactly what is that number? And exactly what is that number? All the specifics relative to this scenario with surface area over here. Okay, go. Tell the person next to you. Everyone's talking to somebody. Find someone to talk to. Okay, where's Ray? Ray Lau, where's Ray? What do you think? So what do these numbers mean? This point, 1.36, 3.5. So when y is 3.5, x is 1.36. Okay? Let's see here. Where's Rithika? You agree with that? When y is 3.5, x is 1.36. You agree? What's that? Okay, y is the independent variable. So which one of these is y? And that's a y or x? Right. So this is the y value on this graph over here. And then we're at 1.36, something like right there. And then what does the 3.5 mean then? Want to keep going? So then 3.5 means what? The total surface area accumulated until 1.36 is y. So can you imagine what surface area that is? Is it the whole thing? So what is a part of it? What part of it is it? What part of the surface is that the surface area of? From y to 1 point, like this, right there? And so we started accumulating. So we're thinking of it accumulating from bottom up. So it's kind of like this much surface area. See that? That much surface area is 3.5, has a 3.5 square units, corresponding to y increasing from 1 to 1.36. Is that what you said? Okay, that's right. So then we changed it up, and we said, all right, let's redo this. We'll still have the same surface, same curve rotated on the x-axis, get the same surface, but let's look at it as f of x is e to the x. That's the same curve, right? It's the inverse function. So then we found the rate of change. We said the radius of that ribbon is the y-coordinate. Now in this case, the y-coordinate is e to the x, right? And so we do 2 pi fx, and this is the rate of change of e to the x, right? Which is e to the x. So I just repeated it because that's the rate of change of e to the x. And then I set up the surface of the area function in terms of x. So that would be the surface area for f from a to x, or of a x, from integral from a to x of the rate of change of surface area for f. So I took this rate of change, put it in there. And so I'm going to graph that on the right-hand pane there. So y apostrophe equals what? This thing, right? Now, one thing we didn't do, when we were graphing these, we should have put a value of a in. Every time we graphed one of these functions with a comma x, we should have specified the value of a. Okay? So what will we specify for the value of a here? If we're accumulating with respect to x. Yeah, so x starts at, so our curve looks like this. X starts at 0. So we're going to do 0, comma, x apostrophe. And that'll be from, so 0. So now x's and x's match up. Our x on the left is the same as our x on the right. Our independent variable over here is x, and we're putting it on the horizontal axis, so all the x's are x's, right? So 0 is less than x prime is less than. So to what x value are we going? So basically, when does ln of y equal 4, right? Because that was this, we went from 1 to 4 in y, but now we're using e to the x. So 4 equals e to the x. So we're going to go from 0 to, see what I'm saying? So the maximum y value was 4. So now what's our maximum x value corresponding to a maximum y value of 4? Natural log of 4, right? Natural log of 4. So we're going to go to natural log of 4. Okay, and we'll graph this different color, say purple, so we know which one's which. All right, so we saw the surface area function for y, so here's the surface area function for x. So what happened? Shouldn't it be the same function? Yes or no?
Why did you switch the axis to the x-axis when you were horizontal on the first graph?
What's that?
Because like when you put the apostrophe,
Uh-huh.
doesn't that switch the axis to the next graph on the next graph?
All it does is graphs this on the right-hand graph rather than the left-hand graph by putting the apostrophes. It's nothing about axes or like the independent variable thing that we're talking about. All it does is, if I took those apostrophes off, then it would have graphed it on this side. So it's just a way to tell GC that I want to graph it in the right-hand side.
Because in the last example, the y-axis was the x-axis.
That has not. There's two totally separate things that the apostrophes has nothing to do with where we're choosing to put our independent and dependent variables. That's totally different. So in the first example, we wanted to take what was on the y-axis and put it on the horizontal axis over there. So we took our independent variable and made it x. But then the apostrophe, all that does is just graph it on the right-hand side versus on the left graph. So it's two different things that you're kind of trying to.
Yeah, because I thought that's what
No, all it means is open up a second window and graph it on the right. That's all the apostrophe means. Nothing to do with our mathematical, like thinking about changing where the axes go with the independent and dependent variables. The two totally separate things. Okay, so now so here is this one. This is the surface area function. Shouldn't it have been the same thing as this one? Why not? Saul, did you say no? Why not? Why should it be different?
Because the ending should be the same, but the beginning is going to be different because y does not start at 0 like x does.
Okay, good. So here y starts at 1 and goes to 4, while x starts at 0 and goes to ln of 4. That's good. And then you said the ending should be the same. Is that right? So what is the ending showing? Why should the ending be the same? Of the whole thing, right? So it's like as you're accumulating in terms of x, you're going to have a different profile of how much you've accumulated as x goes to 0 to ln of 4 versus how much you've accumulated from y equals 1 to 4. But when we get to the end, we've accumulated all the surface, and so the value should be the same. And so in both cases, it's 51.184. Do you see that? So the total area of the surface is 51.1814, and you see that for the maximum x value here, ln of 4, and you see it for the maximum y value of 4. But in between, the way that it gets there is going to be different because it's going to accumulate area totally differently, whether we accumulate from left to right or from bottom to top. Okay, does that make sense? Any questions? Okay, so that is surface area. Let's move on to something new. Last chance.
I do have a question.
Yeah, please.
So why is this any different than the volume accumulation? Why don't we have like two different rates of change or different shapes for the on the accumulation intervals? Why don't we have two different shapes as we did in volume accumulation? Like when you accumulate with respect to x was different than when you accumulate with respect to y.
Because when you do the volume cylinders, those are tied together. You can't. Let's see. Can you do that?
This is different when radius increases or when.
Yeah. So if we rotate about this and say we do cylinders that look like this, okay? So our area of the base cylinders with respect to x. You can't do this with respect to y because you can't do it both ways because this is based on the height increasing and the height is strictly x increasing. So you cannot, you can't do this. You can't, if you're using these kinds of cylinders with the height increasing, you can't then use those same cylinders and change and have it be a change in y. It just doesn't work. But these ribbons, you can, because they're ds, they're like the little hypotenuse, and they're just the ribbons. You can accumulate in either direction. You get the same ribbon. Does that answer it? Yeah. But those cylinders are kind of locked into one of the two independent variables. You can't do it in the other. Okay. Other questions? All right. So let's talk about something totally different. Let's do quantities of motion. Quantities of motion. So we used to have a space shuttle program. Many of you weren't alive when we had the space shuttle program, but you might remember seeing these. The space shuttle, they launched like rockets and they landed like planes. They launched like rockets and they landed like, and they went into space, right? They went into orbit and they helped build a space station, and then they'd come down and they'd land in Florida like a plane. Okay, so here is, this is generally correct. It's not exact, but this is the velocity of the space shuttle every second after takeoff. Okay? So what can you say about velocity? What can you say about the velocity here? Yeah?
Every second it's increasing 30 meters per second.
He said every second it's increasing 30 meters per second. What do you think? So what's that about? So what that thing that he just said? Okay, someone said constant acceleration. What is acceleration? Yeah, so isn't this, so there's a constant rate of change of speed, right? Constant rate of change of speed, because every time a second goes by, the speed goes up 30. Okay, so what's a broader meaning for that? So what's a broader meaning for this idea that every second that goes by, the speed goes up 30 meters per second? Remember? Yeah.
For any change in time corresponds to 30 times that change in speed.
Yeah, so if we're assuming that there's a constant rate of change of speed, then we can say what? For any change in time, right? For any change in time, say dt, then the change in velocity is the rate times, this is like dy equals mdx, right? Given any change in time. So use that fact to find, let's see, is it in there? So what do we know about velocity? It has a constant rate of change of 30 meters per second per second. All right, so I want you to use this, can you use this fact, this, our dv, so dv equals 30 dt. That's our broad meaning for rate of change, constant rate of change, right? Given any change in time, the change in speed is 30 times that. And so, and let's make that 4. So can you use that fact to predict the velocity 4.7 seconds after takeoff? All right, use that fact to predict the velocity 4.7 seconds after takeoff, knowing that at 4 seconds, the speed is 120. So if you knew that at 4 seconds, the speed was 120, and we had a constant rate of change of 30, can you use this principle right there to find the velocity 4.7 seconds after takeoff? All right, so Steve, did you do that?
Yeah.
Tell me.
It's 30 times 0.7 plus 120.
So 120 plus,
30 times.
what do you think? And this is exactly like total accumulation, right? Look, total accumulation, what? Total accumulated up until 4 plus your new accumulated change, right? So this is like our total accumulation. Everything accumulated up to 4 plus the additional accumulation. So we have an additional change of time of 0.7, and we know that we'll get a change in velocity of 30 times 0.7 for that. And so what does that turn out to be? 141? Okay, so these are just basic principles of rate of change, right? Rate of change. And so then, so velocity isn't accumulating, but we can say that changes in velocity are accumulating, right? It's hard to imagine velocity accumulating, all right? But it is, what makes sense is to say changes in velocity are accumulating at 30 meters per second each second. And you guys said this before. What is that then? What is that if the accumulation of changes in velocity is the same as? Acceleration, right? So the acceleration of the shuttle is 30 meters per second per second. So acceleration is rate of change of velocity. Acceleration is rate of change of velocity. Okay, so let's sketch a graph of the acceleration. So acceleration on the vertical axis, time in seconds on the horizontal axis. What will that graph look like? Acceleration. Jennifer, what do you think?
Well, it's accelerating.
Yeah.
Straight line at y is 30.
Okay, so instead of straight, you mean horizontal, right? Yeah, so all lines are straight, but so you're thinking horizontal, right? Yeah, so it's just a horizontal line at 30. If we were to graph the acceleration, so this is a graph of constant rate of change, right? Constant rate of change of velocity. And so our acceleration function is 30 meters per second per second. Okay, we already did this. The meaning of the constant rate of change. So because this velocity starts at 0, not only can we say, we can say that dv equals 30 dt, but because velocity starts at 0, we can also say what? We can have all our changes be from 0, and then our change from 0 is simply what? Wouldn't it just be t? Right? So our change starting from 0 is t. And then our change in speed starting from 0 is just v, right? So because at time 0 we have velocity 0, we can also write this. And that's just like from the table we saw, right? So not only does our constant rate of change tell us that dv equals 30 dt, but in this scenario we can also say v of t equals 30 times t, because at time 0 we have speed 0. Is it fair? If at time 0 we had some other speed to start with, we could still write this for constant rate of change, but we could not write this. Okay, again, the meaning of the constant rate of change is given any change in time, the change in speed will be 30 times that change in time, and since we can say the change from 0 is t, and the change in velocity from 0 is v, we can also say v of t equals 30t. Okay, so that is the speed function. So now I want you to write that speed function again in a different way, v of t. Can you write it where it's representing the net accumulation of tiny changes in velocity? So write this function in a different form that represents or expresses that velocity is the net change of lots of tiny accumulations of change, the accumulation of lots of tiny changes in velocity. Can you do that? Should be able to. Been doing it all semester. So express that 30t in a different way. Express it as the accumulation of tiny changes in velocity. And we'll spin the wheel and see if you got it. Okay, someone back here in this corner. Did one of you guys get it? Guys or gals? I know Samantha's got it. How about somebody else? Right behind Samantha in the sweatshirt. No? How about, tell me your name again in the green shirt? Judith. Did you get it? Oh no. James, did you get it? The accumulation of tiny changes. How do we express the accumulation of tiny changes? There's one thing we should learn right now. Accumulation of tiny changes is integral from 0 to, our independent variable is t. So now it's a little weird. We're going to throw the t here, right? Of what? The rate of change. What's the rate of change? 30. D something else. So I'll say du. Hey, this is what we do in all semester, right? Integral accumulation functions. This is expressing the sum or the accumulation of lots of tiny changes. Each tiny change is m dx, right? Rate times little change in independent. And you get the little change in the dependent, and then you accumulate or sum all those up, starting from 0, and then make it a function up to whatever your value is. Okay, so 2 different ways to express the same thing. And there's advantages and disadvantages to both. Let's talk about this form. Is called the one we've been working with all semester. This is called open form of the accumulation function. What's the advantage of open form? Anyone know? What's the advantage of open form? What's that? This one we can too, right? Yeah, they both can do that. They're both functions, right? They're both functions. We can. Advantage of open form. So the advantage of open form is that it expresses what it's about, right? It expresses that we're summing up like I said, the accumulation of tiny changes in velocity. So it represents the underlying meaning, right? So that notation represents the underlying meaning of an accumulation function. What's the disadvantage to open form? How have we been computing these? What do we have to do? Yeah, Victoria.
We can't do it in our head.
Or right, in our head or by hand,
Yeah.
right? We need technology, right? So we'd have to put this into GC and then have GC do the work for us, which is fine. That's great. But as we'll see later in class, values of the function don't come easily here, right? Values of the function don't come easily. So it's good that it expresses the meaning, but what's the downside is that you can't get values of velocity easily. You need technology to do it for you. Okay, on the flip side, this is called, what's this called? I bet you can guess. Closed form. They're the same function. They're the same function. This is called closed form. What's the advantage to this? Rapid fire results. Like Victoria said, you could do it in your head. You could do it in your head, right? Or if it were a little bit more complicated, you could do it by hand. You could do it, it generates values of the function very easily. Rapid fire. You can get any, given a t, boom, 30 times t gives you the value of the function. So that's what we like about closed form. Open form, we like that it represents the meaning. Closed form, we like that it gives rapid results, right? We get lots of values of the function very easily. So far, every accumulation function we've written, or mostly, has been we always write it in an open form and then we let GC do the work for us. We're coming up in a week or two to a section of the course where, given open form, we're going to learn how to find closed form, right? So that's going to be a whole section of the course. Given an open form accumulation function, can we write it in closed form? It's algebra techniques to do that. Okay, so that's coming up. All right, questions about that? Open versus closed form. All right, so let's look at an example with acceleration and speed. So I got 2 cars here. I guess this is seconds. What's the feet? So this is feet per second per second. this is seconds. So I have a few questions for you. Which car is moving faster at 2.5 seconds? There's 2.5. When will the cars have the same speed for the first time, and when will a car pass the other for the first time? Who will pass who? So let's talk about which car is moving faster at t.25 seconds while I start roll. So you're just, or maybe just the first two questions you can talk about. But the first question, make sure you spend enough time on it. Go, talk. Everyone's talking to somebody. Mortez is going to make sure. Okay, Lauren, what do you think? So, which car is moving faster at 2.5 seconds? What do you think, Lauren? Okay. So isn't it car 2 because car 2, the graph is higher there? Why not? So, because these aren't speed graphs, right? What are these? Acceleration. Okay, so how do we get speed from acceleration? We just talked about it. How do we get speed from acceleration? Speed is, or acceleration.
Accumulation of acceleration.
Okay, so it's not the accumulation of acceleration is the rate. We're not accumulating the rate. We're accumulating small changes in speed using the rate, right? M dx, right? So it's a times dt. So dv equals a, this rate of change, dt. So speed is the result of many little changes in speed, and we calculate each little change in speed by taking the rate times change in time. Gives us a little change in speed. So if we did this from 0 to 2.5, which would have accumulated a greater change in speed? Car 1 or car 2? Car 1, because its acceleration is much higher, so in calculating those little changes in speed, we'd have from here 0 to 2, we'd have much greater changes in speed for car 1 than car 2 because all of its acceleration is higher. Now there's a little bit here where car 2 is greater, but not enough to overtake what's already happened, right? So you should be thinking car 1, and the reason is because if we were to accumulate those changes in speed by taking a times dt plus a times dt plus a times dt, right? Those certainly, the blue graph would give us a greater sum total of these because all of these are higher on the blue graph. Does that make sense? Okay, so when do you think the cars will have the same speed for the first time? Prediction. Okay. No, we don't know. So that's assuming that they started at 0. All right, so, but yes, that's a good one, right? Yeah, sure. All right, so after they start, when do you predict that they'd have the same speed for the first time? Just throw something out. Yeah.
Maybe like 6.5?
6.5. 6, 7, somewhere in there, right? So if you're thinking about, you kind of have to imagine accumulating changes in speed. When are they going to equal out, right? Maybe somewhere 6.5? Any other predictions? 7.25. 5.75. All right, somewhere in this ballpark. All right, how can we find out? So we want to find out. How can we figure this out? Where we want to know exactly when car 1 and car 2 have the same speed for the first time. We've got the tools. Can you problem solve it? Yeah.
Well, couldn't you just set a acceleration function for both of them, and then just take the derivative? And then that would, by setting them both equal to each other and taking the derivative, you can find the time which is both equal.
Take the derivative of acceleration.
Yeah, that would be
No, because acceleration is the rate of change of speed. Acceleration is the rate of change of speed.
Oh, oh yeah.
So we want to, so an algebraic method is going to be difficult here, right? These are, I'll show you the acceleration functions. So they're both, so here's, we got a linear term and a sine term, and then this one has, it's just a cosine function. So you have a cosine function and then a linear plus a sine function. So trying to set equations equal and solve for t is not going to be friendly, okay? So how can we do this? We can do it. We just have to apply what we've learned, apply tools that we've learned. Yeah?
Area accumulation.
What's that?
Area accumulation under the curve.
No, we're not talking about area here. We're just talking about quantities of motion, so it doesn't have to do with area. Not arc length, anybody. So we're talking about speed. We want to know when the velocity is the same. So can we find the velocity functions? How? Yeah, we're going to set up integral functions, and then how can we find out where they're the same for the first time? That's the easiest way. Again, that's going to be very algebraically unfriendly. We've got this awesome tool, the graphing calculator. Graphing calculator. It's awesome. It does amazing things for you. So you don't have to do that crazy, ugly algebra. So set up we got A1 and A2. So can you write the velocity functions for both of these? Go. Just write the velocity functions for both these cars. Hugh. No? Natalia. Alyssa R. Alyssa R. Go, you're writing the velocity function for car 1, velocity function for car 2. Andrew Reed. Andrew. Alan. Alan. Chase R. Oh, Chase. Kayla. Jose. Madison. His name's not here. Christopher Scragg. Stephen Sherman. Samantha's here. Lucas.
Eric.
Lucas. Emily. Kang. Ramiro. Yu Kwao. And Alan's here. Lenoy. Thomas. No Thomas. Okay, Maya, how about did you write the first velocity function for car 1? Integral from? Okay. I think, yeah, so that's what she said. So we're going to do V1. It's going to be A to T. So I'm using T now. Before we used T to be our dummy variable in here, but now we're talking about time, so let's use T for time. That's our actual independent variable. And then we're going to do the integral from A to T of the acceleration u du. Is that what you wrote? Agree with that? And then same with V2. So if you put A to X and then use T's in there, that's fine. As we're doing these quantities of motion, time is our independent variable, so I'm using T now for the independent variable and then using some other dummy variable besides T. Yeah, Nick?
I was going to say, is there any reason to use two different dummy variables?
Yeah, that doesn't matter. I could have used U for this one too, but I just chose a different one because you can. You can choose anything you want. Okay, how are we going to find out when their speed is the same for the first time? Okay, so we'll graph them, and I'll graph it over here. So I'm going to graph speed over here. Okay, so don't look. Source. Okay, here we go. So, which car is which? So I got green and purple. Which car is car 1 and which car is car 2? Tell the person next to you. Which is car 1 and which is car 2? Okay, which car is car 1? It's going faster in the whole beginning part, right? Because its acceleration is generally higher, so its speed is gonna be higher in that first part. So car 1 is the green one, and then car 2 is the pink one, and they have the same speed. First time when? It's fine. 5.625. Who said 5.75? Nick down here. All right. Yeah, so it's at about 5.6 seconds. The speeds of the car were the same at 11.8 feet per second. Okay, so now, last question. When will car... So what are they at the same position at 5.6 seconds? Are they at the same place or is one car ahead? Are they the same place or is one car ahead of the other at 5.6 seconds? People are saying car 1 is ahead. Agree with that? Yeah, because its speed has been greater this whole time. So this is just when their speeds are equal for the first time. But this whole time, car 1 has been going faster. So it's going to be ahead here. So the question is, and then car 2's speed is faster. Will car 2 ever catch back up to car 1? Yes or no? Will car 2 ever reach car 1? Or pass it? Will car 2 reach the same displacement as car 1 and pass car 1 or not? For these, what? 8 seconds. I got it for 8 seconds. Yes or no? Who thinks car 2 will catch up to car 1? Who thinks car 2 will catch up to car 1? Who thinks car 2 won't catch up to car 1? Okay? You are here. Sorry, I didn't see that. All right, well, how can we find out? What's that? All right, so we want to set up the accumulation of changes in position. And the accumulation of changes in position is? Right, integral of speed function. All right, so let's write that. So I've got my speed functions. I think that's it. So then I'm going to show you. Okay, we can do it. Got 2 minutes. Here we go. No. Sorry. Closed. Open. Okay, here we go. About this. Okay, so if we want the accumulation of changes in distance or displacement, then I'm going to do, so there's our, oh shoot. I don't want that. All right, so then here's displacement. It's going to be the integral of the rate of change of displacement, or V, and I got that for both of those. All right, and so notice that I set these up in open form, right? I set these up in open form as integral functions, right? As integral functions. Now watch what happens when I hit graph. I'm going to graph the two displacement functions. Watch. What's going on? Why is this taking so long? Because, why? Because the distance is the accumulation of many small changes in speed, but then the speed was defined as the many small changes of, small changes of speed based on acceleration. So I've got open form double, right? So I've got like 2 layers of open form here. And even for the technology, it takes a long time. Now here I've got these defined in closed form. I've got my distance functions defined in closed form. Okay? So is that complicated? No, that's much, much easier than open form, right? Because it's closed form. It's just constants and sine functions and polynomials. It's not a big deal. Watch. I'm going to graph it. Watch. Ready? Keep your eyes open. I didn't have them both. Sorry. So that's underscoring the difference between closed form and open form. Closed form, rapid results. The graph just instantaneously pops up. Open form, even GC, even technology takes a long time. Did car 2 catch up? You were right. You were all right. Have a good weekend.